And today we're in oligopoly, where we're going to learn the more modern way to model strategic behavior among economic agents, and that is through game theory. Game theory. So I've always hated this name because it seems to belittle this very important topic of strategic behavior. So I like to think of it more generically as the theory of strategic behavior, rather than thinking about it being Monopoly or a board game or Texas Hold'em or something. All of those might be fun, but this particular tool is much more powerful than that. So what game theory is an economic model that shows the interaction among agents. So these are economic agents, and generically that could be firms. Since this is oligopoly, we'll be talking about businesses, but it is much more general than that. It could be people, it could be governments. So organizations. It doesn't have to be just businesses. This particular model, that's part of what makes it a powerful tool, is that it applies to really any sort of situation where there's going to be interaction among the agents involved. So shows the interaction among agents by analyzing moves and counter moves based on expected payoffs. So in the firm's case, the payoffs would be profits potentially. Could be some other things too, but so what I want to do is just jump right into an example. Let's see. Let's try this green here. So suppose we've got two firms. Suppose two firms, Coke and Pepsi, are deciding on whether to go with a high or low advertising budget. Profits are shown in the payoff matrix. Profits are shown in the payoff matrix. Okay, so draw a 4-square box. Something like this. Leave enough room to write something up top and on the sides. And to the left, we're going to be showing the decisions possible for Coke. Coke has the choice of going high or low. has the choice of going high or low. One of the key features of oligopoly was that the firm can no longer make decisions by its own to maximize its own welfare. The decisions made by its competitor are also going to impact its own outcomes. So within these cells are different states of nature after each has made their decision. So Pepsi going high and Coke going high has a certain outcome that we're going to describe here. Pepsi going low and Coke going high has a different outcome. So you start to see how one person's outcome is dependent upon the other person's choice. We're no longer in that profit maximization world of producing the quantity where the revenue generated by the last unit equals the cost of the last unit, where what I choose is what I do and it doesn't matter what other people do. That's changed on us. So for Coke, if both companies go high, Coke makes 20 million and Pepsi makes 20 million. Now, if both companies go low with their advertising budget, they both make more money. Coke makes 50 million, Pepsi makes 50 million. Now the catch is that if Coke spends a good deal of money, gets the Super Bowl ad and some other hot shots to market their product, if they spend a bunch of money on advertising and Pepsi cheaps out and goes low, then Coke makes $100 million and Pepsi makes $0. And the opposite is true as well. If Coke cheaps out, they get 0, and Pepsi hits it big and gets 100. All right, so what's going to happen? What would you predict would be the outcome given this set of circumstances and the choices at hand for each company? Both go low. Okay, why do you say that? They'll both come out ahead, right? Okay. So both low, this outcome is preferred to this outcome, right? Now, is it preferred to this outcome? For Pepsi, for one it is, for the other it isn't, right? So that's kind of what's at hand here as we start to digest this. So one of the things that's going to take you guys some practice is digesting how to analyze the matrix. And so this is an important part. Remember, I've emphasized multiple times how important it is when we look at this particular economic model to think about what are we measuring on the vertical axis, what are we measuring on the horizontal axis, right? And then we've got these different relationships and the way we go. Same thing here, we got to make sure we identify what's going on. So Coke and Pepsi, these are the agents. High and low are the choices for each agent. Within the cell is the payoff. So this is the payoff for the agent listed to the left, the payoff for Coke. So the first entry in the matrix is this agent's payoff. The second entry is the payoff for the agent listed at the top. And the whole diagram that we're looking at is called the payoff matrix. All right, so do you think we might end up anywhere else on the game besides where Shane said both choosing low. Or the flip side is, under what circumstances would we get to low, and what maybe other circumstances might we get to one of the other outcomes?
Maybe high. Both high.
Both high? What would that be dependent upon?
Both of them are trying to get that 100.
All right, if both are trying to go for the 100. So we didn't really give you this information, but are Coke and Pepsi the best of buds? No, they're actually competitors with each other, right? So they're on opposite sides of the fence trying to compete in a competitive market. And so in order to get here, we need a certain level of cooperation between the two, don't we? And if we allow them to work together on this project, would the US government have some issues with that? If the two dominant players in the soda market were to get to jointly pick things, what sort of issues might come up? What are they acting like? Yeah, they're acting like a monopoly. Does that sound very competitive to you? No. So that's the setup that we've got here, is that if they were able to cooperate, they'd essentially be acting as one, acting like a monopoly. So if we end up here, yes, it's a possible outcome, but maybe we would need some level of cooperation between the two. If we start out the game saying that they can't cooperate with each other, how does that change your answer? Would they want to roll the dice on going low? So somebody look at those numbers and say, if we were just going to play the game once, what is the strategy? Put on one hat. Either be a Pepsi person or be a Coke person. And tell me what might be a wise strategy on your part and why.
You go high because you're at least guaranteed 20,000, but a maximum of 100,000.
Good, good, right? So if you go high, did you have your Coke hat on or your Pepsi hat?
It doesn't matter.
It doesn't matter, but what, did you have one in particular? I kind of want to tell the story that way.
Let's go Coke.
Let's go Coke. Okay, so if you're Coke over here, you go high and you'll either get 20 or 100. You go low, you'll get 0 or 50, right? Now, if we take those individually in a little bit different approach and we say, if Pepsi would choose high, what would I want to choose? High or low? If I knew for some reason, or if I predicted Pepsi was going to go high, what should I choose as Coke? High, because 20 is greater than 0. If for some reason I had inside information and knew that Pepsi was going to go low, what should I pick? High. So in either case, it's better strategy for Coke to choose high independent of whatever Pepsi chooses. So we call this a dominant strategy. There's a strategy there that leaves Coke better off no matter what Pepsi does. And that's a good way to start solving these games, to see where we might end up. In a competitive environment, not cooperating, we might end up, or we'd expect to end up here, because Coke has a dominant strategy. Now, put your Pepsi cap on and do the exact same opposite, or exact same thing, but using the Pepsi goggles. If Coke goes low, what would Pepsi want to do? High, because 100 is greater than 50. This is where you got to train your eyeballs on what one to look at. So the second entry is always Pepsi now. 100 is greater than 50, Pepsi should choose high. If Coke would happen to choose high, Pepsi should choose high, because 20 is greater than 0. And so in this particular case, Pepsi also has a dominant strategy. All right, so that's, actually I'm going to hold off writing that down, but we'll write that down in a sec. if this game was played 100 times, so instead of thinking of being a one-shot deal, if we allow the game to be played 100 times, would that change your strategy at all? What might you be tempted to do if you were Coke or Pepsi if there's going to be this game played 100 times?
Might attempt to go low a couple times in a row and see if they would shift over there.
Right, you might try to signal something, right? So these profits are more than double these. And if you're playing it 100 times and we look at the big picture, maybe it wouldn't be too expensive for you to signal to the other person, hey, I'll go low if you go low, hint, hint, wink, wink. We can't write it down in paper or we'll get sued in court by the US government. But maybe we could do that, right? And so maybe we could signal if the payoffs weren't too much that we could play that. So maybe they start doing that early on, and then Pepsi sits back in their chair and start thinking, oh, I got it. I know how I'm going to get Coke. You know, we're kind of did this little signal thing and a little hanky-panky, and we're both doing 50-50. What might Pepsi be thinking to do on the 100th time?
Bounce it back high.
Bounce it back, right? Get that last one. And all of a sudden, Pepsi's like, oh, I got it figured out. So then, Coke says, wait a second. I bet Pepsi's thinking that on the last try, they're going to bounce back. So how might I be able to overcome that? I might bounce back on the 99th one. I'm going to get him. He thinks he's going to get me on the 100th, but I'm going to get him on the 99th. And then Pepsi thinks to himself, wait a second, he's probably thinking that I'm thinking I'm going to do it on the 100th, therefore he's going to do it on the 99th. I'm going to do it on the 98th time. And then who am I on here? Coke thinks back, well, wait a second, he's probably thinking that I'm thinking that he's going to think that I'm going to think on the 97th, 95, 94, 93, 92, right? As we logically unravel this, where do we end up in equilibrium? Right back to here, where we both end up going high. So even if we play it that way, it's possible that we're not going to achieve this equilibrium. And again, maybe we'll get it early on, but then in the long run, it might kind of dissipate back to this behavior, even in that amount of time. Now, does that change if instead of playing it 100 times, we play it indefinitely? We don't know the ending date. There isn't an ending date. Coke and Pepsi have been around for 100 years. Who's to say that they're not going to be around for another 100 years? Does that change the perception or possible strategies? That might, right? Without having that ending date, then that might change things a bit. All right, so we're bringing up a number of issues that we can grapple with in strategy from this very simple payoff framework. So let's just make some notes here on game theory. Number one, is the game played one time, which we'll call a single shot or one shot game. Single shot or one shot is what the lingo is in game theory in economics. So is this a one shot thing, or is it a repeated game? Or is it repeated? If it's repeated, is it played a finite amount of times, i.e. 100 times, or indefinitely, an infinite number of times? Number two, is it a cooperative game or non-cooperative? With companies in the United States, we assume if they're abiding by the law that they're not allowed to collude. So usually non-cooperative with firms, but not always. But that's kind of the rules, one of the rules of the game that we need to know to be informed about it. So usually non-cooperative with firms, in other words, no collusion. Collusion's kind of the fancy word we use for working together on something. Otherwise, they might be acting like a monopoly. All right. With this particular game, would it make a difference if we played it sequentially to where one person makes their choice, the other person knows what the choice is, and then makes their choice, as opposed to both of them making it at the same time or without knowledge of the other? Would that make a difference on the games? If we're playing a sequential game, you go, I go, we kind of take turns, or if we both make our choices simultaneously. Would that make a difference? That would probably make a difference too, right? So that's another element to these games, whether it's sequential or simultaneous. So simultaneous or sequential. So simultaneous means it's not necessarily the same time, but when we refer to it as a simultaneous game, each player makes a choice without knowledge of the other's choice. So each agent makes their choice without knowledge of the other's choice. A sequential game, you know what the other person did. I go, then you go, we take turns. So I go, you go, so we do have knowledge. All right. So all of this leads to a lot of complexity potentially available to analyze strategic behavior. One strategy we looked at was a dominant strategy. A dominant strategy is a choice combination such that one agent is better off regardless of the other agent's choice. Good definition to know for the final exam. How we determined it, for example, for Coke, so from using our numbers, if we're trying to decide if Coke has a dominant strategy, we look at Pepsi's choices and what Coke would do. So for Coke, checking to see if Coke has a dominant strategy, we do this. If Pepsi chooses high, so I got a little bit of shorthand notation here of there's the agent, Pepsi choosing high, so this little arrow here is choose. Pepsi chooses high, then Coke should choose high. Because 20 is greater than 0. If Pepsi chooses low, then then Coke should still choose high. And there's your dominant strategy. A choice combination, a choice in this case, since we only have one step in the game, choose high because it makes Coke better off regardless of what Pepsi does. So Coke is choosing high no matter what. Therefore, Coke has a dominant strategy of high. I'll let you work out on your own. So example number 2 here is for you to do Pepsi. You can write out the same thing if you want, but we come to the same conclusion. And by doing that exercise, if this is a one-shot game, we would predict that high, or the outcomes of 20 million each, would be our equilibrium. So we've got a new context for equilibrium. And I think it'll be helpful for you to think about equilibrium in the most generic way that I did before, a situation in which there's no tendency for change. So, equilibrium, in general, a situation in which there is no tendency for change. I've given you that definition before. But now I want to add one more little definition that's unique to this game theory setup, and it's called a Nash equilibrium. How many of you saw the movie A Beautiful Mind? Russell Crowe, he was the mathematician, economist guy, won the Nobel Prize for what we're going over right now. And his concept was, in fact, one of the things he wrestled with intellectually was that economics seemed to be about a competitive environment, whereas he thought that there's lots of equilibrium that come about through cooperation. And so he kind of struggled with the traditional economic theory at the time. This was developed in about the 1950s and 60s of a lack of academic support for cooperation. Everything was competitive. And so he developed this little simple framework. And his notion of an equilibrium under this context was a choice set or choice combination, such that neither agent or player, wishes to change their choice. Taking as given the other's choice. This concept is often a little bit slippery for students compared to a dominant strategy, but there's a subtle difference here in that you kind of want to say, would I change if I could? Kind of after the fact, analyze that particular solution. So kind of come back to this and say, okay, would Coke want to change their answer if they could, holding this one as constant? No, because 20 is greater than 0. Would Pepsi get a little itchy and want to change their answer, because that wouldn't really be following with what our equilibrium concept is, a tendency for change. Would they want to change, taking as given? No, because 20 is greater than 0. Therefore, it's a Nash equilibrium. Put a little N in the upper right-hand corner is kind of a convention that economists use to show that the Nash equilibrium. Now, using that logic, you can go back to any other cell and check to see if it's an equilibrium. So, as Shane pointed out, is this combination a Nash equilibrium? And so you'd just say, would Coke want to change? And the answer is yes. As soon as somebody would like to change if they could, it's not an equilibrium. It's not a Nash equilibrium. Okay, questions or comments on that? So the reason they titled that, or at least maybe this is part of my interpretation, but the whole beautiful mind thing is really captured here because with this simple little 4-square matrix, we can analyze a ton of strategic behavior, all in this little simple 4-square setup. Could I explain what's going on here to a 6th grader and they might at least kind of catch on with the numbers? This one's bigger than this one and this is what people choose. Yeah, right? It's very simple. A beautiful mind brings complex topics to a very simple structure. And that's what Nash did for us here. One other little side note, this simple little structure has 72 permutations of outcomes. So we're going to do some more here to practice up on this, but I thought it's kind of useful to know this going into it and to harness, or at least think about some of the power of this. So if I make this number bigger than this number, if I make this 150, I've changed the dynamic of the model, right? So that's one. Now I've shown you 2 permutations of the 72 possible outcomes of this simple little setup. So you can go through and do that, and there's some sort of sophisticated statistical formula with using the little exclamation point. Maybe some of you saw that. I wouldn't have any clue how to derive it again, but you can figure out how many outcomes there are, and it ends up being 72. So let's just put that as a little side note. A Beautiful Mind. If you guys haven't seen that movie, you should. Just my humble little opinion. That was Russell Crowe was the main character, being John Nash. I cried during it. It's a tearjerker at different points, and it's pretty awesome. All right, so Beautiful Mind. And then I just want to add this little side note of the 72 combinations. So there are the simple 4-square model has 72 possible outcomes. And outcomes in the sense of this one being higher than this one. There's an infinite number of outcomes if we look at the size of the quantities, what could be involved. But as far as having this one higher than this one higher than this one, 72 possible outcomes. Okay, questions or comments there? All right. So a few years ago, gosh, it's probably been 7 to 10 years ago at Iowa State, I had a nasty little incident where some students were cheating. I'm sure that would never happen here at OU. I'm hopefully crossing my fingers. And it was the final exam. This is a true story. My teaching assistant, I was teaching a, 200-person lecture hall. And one of my teaching assistants bird dogged what he looked like was a little odd behavior going on in the class. And he cleverly grabbed the girl's paper when she turned it in. And then the guy turned in his paper like 20 minutes later. Okay, and then he grabbed that one. And you look at the test and it's like, oh my gosh, this is pretty good evidence that they were just copying off of each other. but, you know, maybe not perfect evidence. So, you know, it's kind of one of those things, well, in theory, I could have said exactly what that person said, or I could have had exactly the same multiple choice problems, right? So, I took a little bit of what I learned in this class on game theory, and I tried to put it to the test. Because what I really needed to get was a confession out of them, rather than to just say, you've been cheating and I'm going to throw the book at you, right? I'd like to get a confession. All right, so let's say it was Pat and Chris. And I'm going to give them some options here, hopefully getting them to confess, but they'd still have the option to hold their honor and deny. And so what I did is I waited till after finals week. I think they took their final on a Thursday. And being the nice guy I am, didn't want to rattle their cage too bad. And again, I didn't have 100% evidence that they were cheating. So I waited till like 11 o'clock on Friday morning when finals were complete. And I called up Pat, and I said, hey Pat, I'm checking into something here. I suspect some cheating going on. But I tell you what, you know the policy on academic dishonesty and so forth, but I at the same time appreciate honesty. And so here's what I'm going to do for you. If you confess to this, I'm going to give you a D for just this test, which isn't going to kill your grade, as you guys know. Some of you might have not scored so hot on one of your exams, but that's not going to kill you, even though the grade itself was like a high D for the test. Now, I didn't really have full evidence on them, so it's possible if they both just denied that they'd still get their B. So what I set up for Pat was I said, well, listen, I'm going to give you this opportunity. I'm going to give the same opportunity to Chris. And here's the deal. If you confess and tell the truth in appreciation of your honesty, I'm going to give you an A. And not only am I going to give Chris an F, but I'm going to turn this over to the university authorities, and they can deal with you however they see fit. And of course, I offered the same thing to Chris, so that if Pat lied and Chris confessed, then he'd get the F and she'd get the A. All right, so I called these two independently. What do you think I got for a result? Confess. All right, well, the story goes on. So now, how did I set things up here? What's the incentives for each? To confess, possibly, right? So let's go back to our dominant strategy. What should Pat do if Pat somehow knew that Chris was confessing? Pat is better off confessing. Now, if Chris is denying, what is Pat better off doing? Confessing. We got a dominant strategy for Pat to confess. And the way this thing is rigged, we got the same thing going on for Chris. She has incentive to confess, possibly to a crime they didn't commit. But I don't know that. I just think they probably did. So this is a famous case that you might have seen in some other classes called the prisoner's dilemma. The prisoner's dilemma. The dilemma is very similar to Coke and Pepsi. The dilemma is that each agent is better off denying the crime. But don't know if they can trust the other. And so what we've got set up here, it's better to confess to something you may not have even done. Now, do the police ever do this type of thing? Yes, they do. This is a well-known trick by the police department. You get, in fact, this little story, it was originally done with two criminals that were busted and they were separated, right? What do the police do if people get, and hopefully you watch Cops and you didn't experience this yourself specifically, but bust a couple people in the act, separate them, right? We don't want them colluding with each other. Hey, I won't tell if you don't tell, I promise. You know, eliminate that right away by separating them out. Okay, so back to our story. I didn't know, by the way, if these two knew each other or not. I didn't know if they were boyfriend, girlfriend, best friends from high school, or complete strangers. I had no clue. All I knew is that my teaching assistant saw what was going on. I don't get to know my students at Iowa State like I get to know you guys, right? So they were just kind of out there, and I didn't know if they knew each other or not. So I called up Pat and explained the terms, and Pat said, no, I didn't do it. I don't know what you're talking about. And I'm like, oh, we got a denier. And I'm like, okay. And then I reiterated the whole setup again. And he said, I'm not going to lie, you know, say something I didn't do. I didn't do it. And I'm like, okay, that's all I need for now. So then I call up Chris, and I give her the same pitch. And she says, I didn't do it. And then I'm like, okay, well, listen, I'm just going to have to turn this over to the authorities, and, you know, you're going to get asked, probably going to need to talk to your parents. And I started kind of laying on exactly what this penalty would amount to. And then all of a sudden, I'm sorry, I never thought about doing it. He didn't know anything about it. I don't even know who it is. And I cracked her. I broke through finally after laying it on, and I got her to confess. And so what she said is she didn't know. She had just sat by him a couple times during the semester, and she had basically just sat there and copied off. But again, I didn't know if they were in cahoots with each other, if they knew each other or not. So now you can see the dilemma I'm in.
Did you give the other guy a bet?
Yeah. Now whose honor do I have to protect? Well, of course, it's mine. So Chris enjoyed her A after cheating miserably off of Pat, and Pat went down the river. Well, you got to do what you got to do. I didn't want to be a liar myself.
That's cold.
I love that story. That brings back some good memories. That's what you call using economics. I want you guys to get to that level where you're not going to learn everything. I know you're going to forget a lot of stuff in this class, but there's going to come that moment where you can say, oh yeah, I know how to handle this situation. All right. No, I didn't give Pat. I sent her down the river. I changed in the back of my mind, I was playing the game fairly. I was just investigating, and so I got the answer I wanted, and I used economics doing it, and so it was pretty awesome. I like to brag about this to other professors and stuff, that I actually use this prisoner's dilemma with the students. So, okay. I think we will wrap up there. We'll see you on Wednesday. Remember.